Hi, this is a short video to show how this Python module to compute directionality spectra works. The module has three functions: the factor, which computes a single directionality factor, the F spectra, which is the function that actually computes the directionality response spectrum, and another function to load earthquake records in peer NGA format. So in this little example, I will show you how to use these functions. First, you will need to import from the module, from the directionality spectra module, you need to import the functions that you are going to use. In this case, I'll be using all three functions. And in addition, I'll be using Matplotlib for the plotting and NumPy for some additional calculations. Okay. So to start, you need to load the two horizontal components of the record you want to analyze. So that's what I'm doing here. I'm loading one and the second horizontal component, which will be saved in S1 and S2. Okay, so let's first calculate the directionality factor for the acceleration trace. So to do that, we use the function dfactor, and all we need to specify here is the two horizontal components that, again, in this case, I have saved in S1 and S2, and then there is a third parameter in which you specify if you want plots to be generated or not. This function has a number of returns. The directionality factor, you have the peak acceleration that is reached and at what angle that acceleration was reached, and also the envelope of the acceleration trace. Now, if you want to calculate the directionality response spectrum, then we're going to use this other function, the F spectra. And for these functions, we need to specify a vector or an array with the periods, which I have calculated here, the periods at which I would like to generate the response spectrum. You need to specify the two horizontal components, S1 and S2 in our case, the damping ratio at which the response spectrum will be generated. In this case, I have specified 5%. The dt, and that's the time between acceleration points. Theta, it will be the angle at which the different angles at which the response is evaluated. In this case, I'm going from 0 to 180 in 1 degree increments. And finally, if you want or not to generate plots. What this function returns, it returns the ROD-D100 response spectrum, the ROD-D50 response spectrum, the ratios between ROD-D100 and ROD-D50, and the directionality response spectrum. So if we run this, what we get are two figures. The first one, this one, coming from the first function we use, dfactor, is showing the acceleration trace in polar coordinates, which is the blue line. It also identifies the peak acceleration that was reached, in this case 0.2, and it happens at 46 degrees. Okay, and it also shows you the directionality factor that was calculated, in this case 1.39. How we calculate this directionality factor? We take the area of this orange circle, which is a circle with a radius equal to the peak acceleration, and divided over this blue area, okay, which is the area of the envelope of the acceleration trace. Then we take the square root of that ratio, and in this case we get 1.39. So obviously a value close to 1 implies little to non-directionality, and a largest value imply more directionality. For the second function, we get this plot, which is showing the ROD-D50 and ROD-D100 response spectrum. The figure below shows the ratio between ROD-D100 and ROD-D50, which is another way to estimate the directionality in the ground motion. And the bottom figure shows what we are proposing, which is the directionality response spectrum. So basically, we are applying the same concept to the response of different single degree of freedom system of different periods, and generate this directionality response spectrum. And I think that's it. I hope it helps.